All right, so this is going to be our walkthrough for the homework assignment titled More Limit Proofs. This is just a bunch of practice with delta epsilon proofs or proofs involving n and m. So we're going to start off with a few easy ones and then work on to the infinite ones, which are a little more difficult. So this one's just a linear one. The limit as x approaches 2 of 3x plus 1 equals 7. And so the way we always start these is with our given, right? So we're going to start with given and epsilon greater than 0. We want to choose delta equal to something, which we'll figure out in a second. And then the supposed statement for all of these delta epsilon proofs, the regular ones, it always is 0 is less than the absolute value if x minus our a value, which in this case is 2, is less than delta. So this part doesn't change for any of the delta epsilon proofs, any of the ones that don't have an n or an m in them, right, with no infinities. And then what we want to show is that the absolute value of our function minus the limit, so 3x plus 1 minus 7, is eventually less than epsilon, where epsilon can be written in terms of constants and delta. So that's our goal. So in order to do that, the first thing we're going to do is just simplify the absolute value down. So we have the absolute value of 3x minus 6, right, if we just do the 1 minus the 7. And then we should see that we can factor the 3 out of that. And one of our rules for absolute value is that if I have two things being multiplied together inside of an absolute value, we could separate those into their own absolute values. And of course, the absolute value is just 3. So we now have 3 times the absolute value of x minus 2. Well, we already know that the absolute value of x minus 2 is less than delta. So 3 times the absolute value of x minus 2 must be less than 3 delta. And now we've pretty much completed the proof. We've gotten this absolute value of f of x minus l to be less than something that is written in terms of constants and delta. So we just set that equal to epsilon, right? If I say let's let 3 delta be epsilon, then delta, the delta that we want to choose, is just epsilon over 3. So this is equal to 3 times epsilon over 3, which is epsilon. So our choice for delta is just epsilon over 3. And that's the proof. For our next one here, again, it's just a linear one, so it's going to start off nice and easy. We'll start off with given epsilon greater than 0. We're going to choose a delta equal to something. And then we'll suppose that the 0 is less than our absolute value of x minus negative 1. Well, x minus negative 1 is x plus 1 is less than delta. Right, and that's just our delta tolerance statements. It's saying that we are within delta of negative 1, right? We're a little bit to the left or a little bit to the right of negative 1, that a value that we're approaching. And then what we're going to show is that the absolute value of our function minus the limit is eventually less than epsilon. And again, this is our epsilon tolerance statement. It's just stating that the function will always lie between a little bit above and a little bit below what that limit is, right? Within epsilon of that limit. And so we'll simplify what's inside the absolute value into negative 5x minus 5. And then we'll recognize that we can factor a negative 5 out of that, giving us negative 5 times x plus 1 inside the absolute value. And just like in the last problem, we can separate that into two different absolute values. And of course, this time, the absolute value of negative 5 is positive 5. So we have 5 times the absolute value of x plus 1. And so now, that matches up again really nicely with our delta tolerance statement. And that's what should always happen with these linear ones. And even with the quadratic and the cubic ones, we should get a piece of it at least that matches up with that. And so we can just say that 5 times the absolute value of x plus 1 is less than 5 times delta. And if we then let 5 delta equal epsilon, then delta should be epsilon over 5. So we'll say 5 delta is 5 times epsilon over 5, which is epsilon. So our choice for delta is 1/5 of whatever epsilon is. So in other words, like practically speaking, what this means is as long as we want to be, whatever our epsilon is that we want to be within, whatever epsilon tolerance range we want for our limit, and we can be epsilon above the limit and epsilon below that limit, we want delta to be 1/5 of that, right? If we restrict the x values to 1/5 of what we restricted the y values to be, the function values will always fall between L plus and L minus epsilon. All right, for number 3 here, we've just got a quadratic. So again, the start's going to be the same. We're going to be given an epsilon greater than 0, and we're going to choose a delta equal to something. And then we'll suppose, again, the same thing. All of this is all going to be the same for all of the delta epsilon proofs, all the ones that don't involve infinity in any way. So we're going to suppose that 0 is less than the absolute value of x minus a, which is 2, is less than delta. And then we want to show that the absolute value of our function, x squared minus 5x plus 1, minus the limit, so minus a negative 5, so plus 5, is eventually less than epsilon. So again, we'll simplify what's inside the absolute value first into x squared minus 5x plus 6, and then we'll factor that. And when we factor it, it'll be 2 terms inside the absolute value being multiplied together. So we can just separate them into 2 separate absolute values, right? It's absolute value of x minus 2 times the absolute value of x minus 3, because that's what x squared minus 5x plus 6 factors to. Well, we'll note that a piece of this, the absolute value of x minus 2, matches up with our delta tolerance statement. So if I just multiply both sides of my delta tolerance statement by absolute value of x minus 3, I'd get the statement that the absolute value of x minus 2 times the absolute value of x minus 3 is less than delta times the absolute value of x minus 3. So we've made some progress here, but we've still got this x minus 3 term inside the absolute value. So what we need to do with that is we need to set a little restriction on delta. And when we do that, we always have to put this minimum in here. So we're gonna say, let's let the absolute value of x minus 2 be less than 1. Right, so we're just saying at a minimum, at a maximum, basically, we're going to let delta be 1, which is a pretty wide range for delta. And in practice, right, our deltas are always going to be much smaller than 1, right, because we want to restrict this to a really small interval. And so, and we write minimum because we're going to be choosing the minimum between 1 and something else over here. So what I'm saying is that the 1 is the largest this thing could possibly be, because if the other piece that I put in there is smaller, then I'm going to choose the smaller one. And if the other piece that I put in there is bigger, then I'm going to choose 1. So the largest we're going to ever let delta be here is going to be 1. So if we undo this absolute value, we end up with this statement. And if I subtract 1 more from this, and if I subtract 1 from all the sides of this, I'll get negative 2 is less than x minus 3 is less than 0. And so what we're looking at there then is that the x minus 3 is between 0 and negative 2. And so I'd like to be able to figure out what that means about the absolute value of x minus 3. Well, if I had something like this, let's just say I had this, negative 2 is less than x minus 3 is less than 2, then I could say that the absolute value of x minus 3 is less than 2. I think that would be a true statement there, right? And so, because that's exactly how that resolves itself, right? We can undo that absolute value in that manner. Well, if I look at the statement I have up here, I have the x minus 3 is greater than negative 2, which is exactly what I have here. So that piece of it is satisfied. And I also have x minus 3 is less than 0. Well, if x minus 3 is less than 0, it had better be less than 2, right? I mean, that's just how math works. If I have a number that's less than 0, that number is also less than 2. So if I'm satisfying everything up here in this inequality that I wrote in red, then I'm also satisfying everything in this inequality down here, which means that if this is true, then this is true. And if that inequality down here is true, then this absolute value inequality is also true, that the absolute value of x minus 3 is less than 2. And so I can just say that this is now less than 2 times delta. And if I let 2 delta equal epsilon, then epsilon should be delta over 2. And so what we're going to say is that this is less than 2 delta, which is less than or equal to 2 times epsilon over 2, which is epsilon, which is slightly different than the previous ones, right? Where I have this less than or equal to in here. And we'll talk about why that is. Let me write my epsilon over 2 up here first. And that's the end of our proof. The reason why it's a less than or equal to rather than just a less than like it usually is because it depends on whether I choose the 1 or the epsilon over 2 as my delta. Right? So if I choose the epsilon over 2 as my delta, then those are just equivalent statements, right? 2 times delta is 2 times epsilon over 2. Delta is epsilon over 2. But if I choose the 1 value, right, as my delta, then really what I'm looking at is 2 times delta is less than 2, which 2 times epsilon over 2, right, which must be true because I know that the 1 was less than epsilon over 2. And so I'm picking something that makes that a less than value. And so that's the reason why. We can show it out algebraically. I did that in the lectures, and I think I did that in some of the previous assignments. But you just kind of got to remember now that anytime you do this transition from the 2 delta to the 2 times epsilon over 2 or whatever it might be, it's always got to be a less than or equal to if you've got a choice over here between 2 values for delta. All right, so for number 4 here, we're going to start the same way with a given epsilon greater than 0. We're going to choose delta equal to something. And I can tell you right off the bat, since this is a quadratic, the method we're going to use to solve this is going to give us this minimum thing in here. And so we'll suppose that 0 is less than the absolute value of x minus a, which in this case is 3, is less than delta. Then the absolute value of f of x minus L must eventually be less than epsilon. Well, x squared minus 5 minus 4 is just x squared minus 9. And x squared minus 9 factors into x plus 3 and x minus 3 using a difference of squares. And again, since we can be factored together inside the absolute value, they can be separated into 2 separate absolute values. Since we know that the absolute value of x minus 3 is less than delta, then we know that absolute value of x minus 3 times something should be something that's positive, should be less than that same positive thing, the absolute value of x plus 3 times delta, right? I'm really just taking this inequality and multiplying both sides of it by absolute value of x plus 3 to get this is less than this. All right, so now we're going to have to do some of the same work off to the side that we did previously. We know that we're gonna make this choice here. I'm gonna say let's let the absolute value of x minus 3 be less than 1, and 1 is just usually a nice easy number that works. So I'll pick 1, and if something weird happens with the inequality or you can't deal with it, then that's okay. And you can pick a different number. So we end up with -1 is less than x minus 3 is less than 1. And we want to turn this into an x plus 3 this time because that's what's left over here in our proof, right? Is an absolute value of x plus 3. So in order to turn that into an x plus 3, I just got to add 6 to everything, which would be 5 is less than x plus 3 is less than 7. And so this time, I think I should be able to see that if I had this statement, x plus 3 is less than 7 greater than -7, that's the same as the absolute value of x plus 3 is less than 7. And that's exactly what we have here, except that we've got the x plus 3 is less than 7 very clearly. If x plus 3 is greater than 5, it must also be greater than -7. So anything that satisfies the inequality down here also satisfies, or sorry, anything that satisfies our inequality up here also satisfies this one down here, which means that this is also satisfied by everything we've said up here. So if the absolute value of x plus 3 is less than 7, then this should be less than 7 delta. And now we just let 7 delta equal epsilon, giving us epsilon is, we already have epsilon, giving us delta is epsilon over 7. So this is now less than or equal to 7 times epsilon over 7, which is just epsilon. All right, for our next one here, we've got a cubic function here, but the process is going to remain pretty much the same, at least from the start. We're going to be given our epsilon greater than 0. We're going to choose a delta equal to something, which we'll figure out in a second. And we'll suppose, still exactly the same as before, that 0 is less than the absolute value of x minus a, which is 2 this time, right? X is approaching 2, and then is less than delta. And so then the absolute value of our function, x cubed plus 3x squared minus 4x, minus our limit, 12, needs to eventually be less than epsilon. So this function inside the absolute value looks like it factors out pretty nicely by factoring by grouping, right? If we factor an x squared out of the first two terms, we get x squared times x plus 3. And if we factor a minus 4 out of the last two terms, we get minus 4 times x plus 3. And because those x plus 3's match up nicely, we can rewrite this as the absolute value of x squared minus 4 times x plus 3. And we can then, we should be able to rewrite that with further factorization of x minus 2, x plus 2, and x plus 3. And so this time we can see that we do have a piece that matches up again, right? Just like we always should. The absolute value of x minus 2 is less than delta. So this must be less than delta times the absolute value of x plus 2 times the absolute value of x plus 3. And so we're going to do the same work as before. We're just going to say, well, let's let the absolute value of x minus 2 be less than 1, which gives us this statement over here. And doing that means we have to write minimum between 1 and something. And now we just need to build in an x plus 2 and an x plus 3 into this. So we'll start with the x plus 2. We'll add 4 to everything. So that'll be 3 is less than x plus 2 is less than 5. And we should recognize, kind of like the last ones, that, if I had x plus 2 is less than 5 and greater than negative 5, that'd give us the absolute value of x plus 2 is less than 5. And so we're going to eventually replace that x plus 2 with 5. And we can also, from right here, turn this into x plus 3, we add 5 to everything, is less than 6 and greater than 4. And if that's true, then x plus 3 must be less than 6 and greater than negative 6, which means that the absolute value of x plus 3 is less than 6. So the absolute value of x plus 2 is less than 5, and the absolute value of x plus 3 is less than 6. So this is less than delta times 5 times 6, or 30 delta. And so if I let 30 delta equal epsilon, then delta is just epsilon over 30. And we can say this is less than or equal to 30 times epsilon over 30, which is just epsilon. And so we'll fill in the epsilon over 30 up there for our proof, and that's it. That's all we need to do for this one. All right, for our next one, another cubic, we're going to start off exactly the same way. We're going to start off with given an epsilon greater than 0. We're going to choose a delta equal to something. And we'll suppose, again, exactly the same, that 0 is less than the absolute value of x minus a, or x minus negative 2. which is x plus 2, is less than delta. Then the absolute value of x cubed minus 4 minus negative 12, so plus 12, needs to eventually be less than epsilon, right? That's the same process as all these other proofs. So we'll simplify down what's inside that absolute value. It'll become x cubed plus 8 inside of there. And we can then factor that using the sum of cubes into an absolute value of x plus 2 times an absolute value of x squared minus 2x plus 4. And again, you need to know the sums and differences of cubes for this test. So from there, we now should hopefully see that we have the x plus 2 is less than delta, which means that this is less than delta times the absolute value of x squared minus 2x plus 4. And from there, what we can do is we can do this nice little thing here that there's something called the triangle inequality, right? And the triangle inequality, which you don't need to state that you're using it, but the triangle inequality says the absolute value of a plus b is always less than or equal to the absolute value of a plus the absolute value of b. And we kind of talked about why that's true in class. I did a little proof of it in class, just kind of tested all the different cases. So I could say that what I've got there is less than or equal to delta times the absolute value of x squared plus the absolute value of negative 2x, right? Because plus a negative 2x is the same as minus a 2x. And then plus the absolute value of 4, which a lot of that can just be simplified down, right? This is equal to delta times the absolute value of x squared is just x squared. And then the absolute value of negative 2 times x, well, I'm going to just kind of write this right here. That's the absolute value of negative 2 times the absolute value of x. Well, the absolute value of negative 2 is just 2. So this is plus 2 times the absolute value of x. And then the absolute value of 4 is just 4. And so now all we have to do is figure out a relationship between x and some value, or the absolute value of x and some value, and x squared and some value. And the way we're going to do that is with that same side work that we've normally been doing. We're just going to now put a minimum here, a minimum between 1 and something. And we'll say the absolute value of x plus 2 is less than 1, which means that negative 1 is less than x plus 2 is less than positive 1. And now we just need to first of all, we'll get an x in the middle so we can deal with the 2 absolute value of x. So in order to do that, we need to subtract 2 from everything. And so that'll give us x is less than negative 1 greater than negative 3. Right? And if x is between negative 1 and negative 3, well, that should tell us that if this is true, right, if this is true, then x is greater than negative 3, but also less than positive 3, right? Because if I'm less than negative 1, I must also be less than 3. So the absolute value of x is less than 3. And also, if this is true, if x is between negative 3 and negative 1, then x squared is going to be less than 9 and greater than 1, right? If I'm between negative 3 and negative 1, the squares of those are going to be between 1 and 9. So I now know that x squared is less than 9 and that the absolute value of x is less than 3, which means I can go in and I can say that what we've got over here, our delta statement, is now less than delta times, well, x squared is less than 9, so I can put a 9 in here. And 2 times the absolute value of x should be less than 2 times 3, because the absolute value of x is less than 3. And 4 is just 4. Well, if I add all of those together, I get 19 delta. And just like we've kind of done off to the side for all these other ones, we've said, well, let's just let 19 delta equal epsilon. So delta is epsilon over 19. So this is now less than or equal to 19 times epsilon over 19. And again, it's a less than or equal to because we're having this choice between 1 and epsilon over 19. And dependent on which one we choose, it's either the less than or the equal to here. And that's the end of that proof. All right, here is our first one on this assignment that is not a delta epsilon proof. Right, this one we have x approaching infinity, which means that it is, this is an N-Epsilon proof. Anytime we have x approaching positive or negative infinity, we use N. And we're going to start off with the same thing, though. We're going to start off with our given epsilon greater than 0. So anytime the limit is approaching a real number or equaling a real number there, then we always start off with given epsilon greater than 0. And now we're going to choose, instead of delta, we're going to choose n, because we're going to use n for deltas. And so we're choosing n equal to something, which we'll figure out in a minute. And our suppose statement changes now. Anytime it's x approaches infinity, the statement is x greater than n greater than 0. And if we were approaching negative infinity, then it'd be x is less than n is less than 0. But then our then statement and the rest of our work should be pretty similar, right? The then statement is the absolute value of our function minus our limit needs to eventually be less than epsilon. And this time we want to write epsilon all in terms of constants and n. So we'll do the same kind of thing that we did before. We'll just simplify what's inside the absolute value first. We'll start off by getting a common denominator here, right? We'll multiply this by x over x. So this becomes the absolute value of 2x minus 2x cancels out, and we just end up with 3 over x inside that absolute value. And so then from there, well, the absolute value of 3 part is no problem, but the absolute value of x, well, what do we know about x? We know that x is greater than 0. So if 3 is positive and x is positive, everything inside that absolute value is positive, which means that I can just pull it outside of the absolute value. And so I just have 3 over x. Well, off to the side, we'll note that x is greater than n, right? Which means that 1 over x is less than 1 over n, which is exactly what we want, right? So 3 over x is now less than 3 over n, right? I could just multiply both sides of this by 3 to get that statement. So we have 3 over x is less than 3 over n, and now we can just set 3 over n to be epsilon, giving us n is equal to 3 over epsilon. So this is equal to 3 over epsilon, which is just epsilon. So our choice for n is 3 over epsilon. And that's the entirety of that proof. All right, our next one here, we have a limit as x approaches negative infinity of a function is equal to a real number. So this is another one that's n and epsilon. So we'll start with given an epsilon greater than 0. We want to choose n equal to something. Supposing that, in this case, since x is approaching negative infinity, we're going to say x is less than n is less than 0. And then we want to show that the absolute value of our function, 4x squared minus 1 over 3x squared plus 5, minus our limit, which is 4/3, is eventually less than epsilon. So what we'll do is we'll start off by getting a common denominator, just like we did in the last one, to combine the two fractions together, which means I'm going to multiply the 4x squared minus 1 by 3, over 3, and then the minus 4 by 3x squared plus 5 over 3x squared plus 5, giving me this. Right, that'll be what we get with a common denominator. 3 times 4x squared minus 1 minus the 4 times 3x squared plus 5 all over 3 times 3x squared plus 5. And then we'll simplify down what's in our numerator. So this is 12x squared, and this is negative 12x squared. So those are going to cancel out. And so then we're going to have a negative 3 minus 20. So this is actually equal to the absolute value of negative 23 over 3 times 3x squared plus 5. And we should note that what's in the denominator here is always positive, because if I take any x value, even if it's negative, right, because I have a negative x value, and square it, I get a positive. If I multiply by 3 and add 5 and then multiply by 3 again, it's still positive. So the denominator is positive, but the numerator is negative. So this whole fraction is actually a negative value. And so to take it out of the absolute value, I just make it positive. And I'm going to distribute that 3 times the 3x squared plus 5 this time. I'm going to make this 9x squared plus 15. So we've now got that our absolute value statement there, f of x minus L, is just equal to 23 over 9x squared plus 15. And from there, that's all in terms of constants and x. So we should hopefully be able to come up with a relationship here for x and n, or for x squared and n squared, that hopefully will be useful for us. So we know that, off to the side here, x is less than n, which is less than 0, right? Which means that x and n are negative numbers, which means that if I square them, we actually have to flip the inequality sign, right? If you think about it, like let's say x was -2 and n was -1, right? When I square them, even though x is less than n, when I square them, x squared is greater than n squared. So, right, because you get 4 is greater than 1. So really what we've got here is that x squared is greater than n squared. And if that's true, well, I should be able to just multiply both sides of this by 9 to give me the 9x squared that I have down here. And I should be able to add 15 to both sides. Maybe. It'll let me right there. Let's try that again. All right. And then we can take the reciprocal of both of these to get 1 over 9x squared plus 15 is now less than 1 over 9n squared plus 15. Well, that means that 23 over 9x squared plus 15 is less than 23 over 9n squared plus 15. And from there, we could just immediately solve this, just set that equal to epsilon. But we can also just kind of simplify this down a little bit as well. Right? If I have 23 over 9n squared plus 15, something that has a smaller denominator, right? If I have something with a smaller denominator, it should give me a larger value. So if I make this denominator smaller by getting rid of that plus 15, that number should actually be a bigger number, right? And I could do the same thing, right? If I'm multiplying n squared by 9, well, then that's going to be a bigger number than if I don't multiply by 9, right, in the denominator, which makes the actual thing less than. So if I could say this is also less than 23 over n squared, and that's probably good enough. So we can now just say, let's let 23 over n squared equal epsilon. So we end up with n squared equals 23 over epsilon. And when we square root, we get n equals positive or negative root 23 over epsilon. Well, now we have to think about which one do we want to choose. And our first instinct is probably to choose the positive one, but that would be wrong, because we know that n is less than 0 from our very beginning, which means we need to pick the one that is negative. So this is equal to 23 over n squared, which is negative root 23 over epsilon squared, which just equals epsilon. So our choice for n is just going to be negative square root of 23 over epsilon. And again, we're making that choice because we know that n must be less than 0. All right, for our next one here, we've just got another, this is another N-Epsilon proof. So we're going to start with given epsilon greater than 0. We're going to choose n equal to something. And suppose that 0 is less than, well, we're not supposing that. We're supposing that since this is an n proof, sometimes I get in that habit, we're going towards infinity. So x is greater than n is greater than 0. Remember, anytime we're doing x approaches infinity, it's always x greater than n greater than 0. And then we will take the absolute value of our function minus the limit and show that it is eventually less than epsilon. And so we can immediately get rid of that minus 0, of course. And the denominator of this fraction is always positive, but the numerator is not always positive. So we can't just pull it out of the absolute value. But we could pull it out of the absolute value if we made sure that x was always greater than 7/3, right? This whole thing, this fraction, our function, is greater than 0 if x is greater than 7/3. So let's just put that restriction on x, which means that when we do that, if we say that if x is greater than 7/3, that means that the smallest value that we could possibly have for n now is going to be 7/3, right? And then that will allow x to be more than 7/3. And so, so we're going to say the max between 7/3 and something. And that allows us to just pull that completely out of our absolute value. And now we can start to manipulate this a little bit. Kind of like we did in the last one, we can say that this is less than 3x minus 7 over a smaller denominator, right? If I have a smaller denominator, it gives me a bigger value, especially when we're dealing with positive numbers. So I could get rid of the 4x and I could get rid of the 1. I could just call this 5x squared down here. And the reason that we're going to want to do that is because we'd like to also simplify that numerator down. And if we think about simplifying that numerator down so that we can get rid of all the constants other than the coefficient on the x, we could then cancel some x's out. And we'd like to end up having an x in our denominator because we need a less than sign, and we have x is greater than n. And so we want to be able to take a reciprocal to get 1 over x is less than 1 over n. So if we think about this a little bit further, right, something that would make this fraction bigger is if the numerator was bigger. Well, what's bigger than 3x minus 7? Well, 3x minus 6 is, and 3x minus 5. The less I subtract, the bigger it gets. In fact, if I subtract nothing from it, it should get bigger also. So 3x minus 7 over 5x squared ought to be less than 3x over 5x squared, which is now just equal to 3 over 5x. And, well, since we know that x is greater than n, we know that 1 over x is less than 1 over n. So we can say that this is less than 3 over 5n. And if we just let 3 over 5n equal epsilon, then we end up with n is equal to 3 over 5 epsilon. So we'll say this is equal to 3 over 5 times n, which is 3 over 5 epsilon, which is equal to epsilon. And so as long as we choose the maximum between 7/3 and 3 over 5 epsilon, then our proof is complete. All right, this is our first one that is an M proof, right? So this is equaling negative infinity. So if it equals negative infinity or positive infinity, we use M instead of epsilon. And it's going to be a delta proof because we're approaching a real number. So for these ones, our setup is going to be given an m greater than 0 or an m less than 0. So if x or if our limit is equal to infinity, it's going to be given m greater than 0. But our limit here is equaling negative infinity, so we're going to be given an m less than 0. And then we want to choose our delta. So we're going to choose a delta equal to something, which we'll figure out in a minute. Now our suppose statement goes back to that delta tolerance. So it's suppose 0 is less than the absolute value of x minus 4 is less than delta. Then, now instead of it being the absolute value of f of x minus our limit, since our limit is non-existent, it's negative infinity, it's just the function itself needs to eventually be less than m because we have a negative infinity. we would have a greater than m in the end if we were equaling infinity. But we're equaling negative infinity, so it just needs to be a less than m. So we need to show that 2x over x minus 4 is less than something in terms of deltas and constants. Well, we should be able to note here that if x is approaching 4 from the left-hand side, that means that x is less than 4, or that x minus 4 is less than 0, which will allow me to take this absolute value away on this statement. Okay? And the reason I want to do that is because down here I have an x minus 4, but it's not inside an absolute value. So I need to clear off that absolute value. So if x minus 4 is less than 0, then the absolute value of x minus 4 is the opposite of x minus 4. So the opposite of x minus 4 should be less than delta, right? From this statement right here. Well, if that's true, then x minus 4 is greater than negative delta, and 1 over x minus 4, which is pretty much what I have over there, should be less than negative 1 over delta. So now I can replace this with less than 2x over negative delta. And we just then need to figure out what is 2x less than, right? Well, 2x, if we want to go up here and sort through that, like 2x is, if x is less than 4, then 2x should be, we would think 2x should be less than 8, which is true. But if I take that 2x is less than 8 statement from here, right, if I say 2x is less than 8, that kind of creates a problem for us because I need to divide by negative delta, right? And so if I divide by negative delta, I can't keep that less than sign there. I would have to flip to a greater than sign. So that's not going to work for us. So what we need to do is we need to put a little restriction on here. And so we're going to just say a minimum between 1 and something, which means what we're going to do is we're going to say that the absolute value of x minus 4 is less than 1. And if that's true, right, then negative 1 is less than x minus 4 is less than 1. And to turn that into just an x, that would give me x is less than 5, but greater than 3, which tells me that 2x is less than 10, but greater than 3, which tells me that the only piece of that I really care about is that 2x is greater than 3. So if I'll work that over here. If I have 2x is greater than 3, right? Well, not greater than 3, greater than 6. 2 times 3 is 6. So if I have 2x is greater than 6, then when I divide those both by negative delta, 2x over negative delta should be less than 6 over negative delta. So I can say this is less than 6 over negative delta, which will allow me to finish off this proof here. Right? I can replace the 6 over negative delta with m, right? Which means that m is going to be delta is going to be negative 6 over m. So this is equal to 6 over negative 6 over m, which is just m. So we'll choose the minimum between 1 and 6 over, or negative 6 over m as our delta here. All right, so our next one here is a limit as x approaches 2 from the right of 2 over 5x squared minus 20 is equal to infinity. So for this one, we're equaling infinity, which means it's an m proof, and x is approaching a real number, which means it's a delta proof. So this is a delta m proof, and since it equals infinity, we'll start with given m greater than 0, and we will choose delta equal to something, which we'll figure out in a little bit what that's going to be. Our supposed statement is going to be our regular delta tolerance statement. 0 is less than the absolute value of x minus a, which is 2 in this case. is less than delta. And then our function, 2 over 5x squared minus 20, we need to eventually show that that's greater than m, right? Because we want to show that this is going towards infinity. So our first step here is just going to be to factor out that denominator. Right? The denominator factors to 5 times x squared minus 4. Right, that's 5 times x squared minus 4 down here, which is 5 times x plus 2 times x minus 2. And so we should see then that we can clear out the absolute value from our delta tolerance statement off to the side, knowing that x is approaching 2 from the right-hand side tells us that x is greater than 2 or that x minus 2 is greater than 0. And if x minus 2 is greater than 0, then we can clear that absolute value off and get that x minus 2 is less than delta. And if x minus 2 is less than delta, then 1 over x minus 2 is greater than 1 over delta, just by flipping the inequality sign there when we take the reciprocal. And we should end up then with this is greater than 2 over 5 times x plus 2 times delta. And from there, we need to do a little bit of work to figure out what x plus 2 is greater than. So in order to do that, we're going to set this restriction like we've done in the past, a minimum between 1 and something else here. And if we had x minus 2, so we'll do if the absolute value of x minus 2 is less than 1, then x minus 2 is between -1 and 1, or x plus 2, if we add 4 to everything, is between 5 and 3. Well, if x plus 2 is less than 5 and greater than 3, it must also be greater than -5, which gives us the absolute value of, oh, actually, we don't even need the absolute value. We just have x plus 2 is less than, I was thinking we needed to go into an absolute value here, but we don't actually need to do the absolute value. We'll just stick with our x plus 2 is less than 5 greater than 3. If x plus 2 is less than 5, then that tells me that 1 over x plus 2 is greater than 1 over 5. And so I can now replace that x plus 2 that's in the denominator with a 5 and say that this is greater than 2 over 5 times delta, or 2 over 25 delta. And so what we end up with there then is we'll just let 2 over 25 delta equal our m, which means that delta is equal to 2 over 25m, making this 2 over 25 times 2 over 25m, which just undoes to become m. So delta is the minimum between 1 and 2 over 25m. And our next one here is another m proof because it equals infinity, and it's a delta proof because our a value is 0. Right? And so we're going to be given an m greater than 0. We want to choose delta equal to something, supposing that we have 0 is less than the absolute value of x minus 0. I don't need to write that, is less than delta. We just have that the absolute value of x is less than delta. And then we need to show that our function 2x plus 1 over x squared is eventually greater than m. And so in order to do this one, we're going to start off with kind of putting a restriction on this so that we can deal with this 2x plus 1 that's in our numerator and with the x squared that's in the denominator at the same time. Right? So the restriction that we're going to put on this is we need something in here that when I undo it is going to show me that 2x plus 1 is greater than something else. So we're going to start off by saying that let's suppose that delta was equal to 1/4, which would give us the absolute value of x is less than 1/4, which means we need to put a minimum on here. just a minimum between 1/4 and something is what we're going to have in our final result of our proof. And so if x is approaching 0 from the left, that tells us that x is less than 0, which means that the absolute value of x being less than 1/4 actually tells us that x is greater than -1/4. And if x is greater than -1/4, then 2x must be greater than -1/2. And 2x plus 1 must be greater than +1/2 if we add 1 to both sides. And so if 2x plus 1 is greater than 1/2, I can just divide both of these sides here by something that is positive, namely x squared. And so I can divide the 2x plus 1 by x squared and the 1/2 by x squared, giving me 2x plus 1 over x squared is greater than 1 over 2x squared. And so once I have that, now everything is all in terms of just x, and I should be able to rewrite that a little bit further by noting again that since x is less than 0, right, if x is less than 0, then our absolute value of x is actually -x. So -x is going to be less than delta, just by using our delta tolerance statement. And when I square both sides of this, this is -x being squared, right? So what we're doing there is we're multiplying by something that's still positive, right? So we end up with x squared is less than delta squared, which tells us that 1 over x squared is greater than 1 over delta squared, which will allow us to replace this with a greater than 1 over 2 delta squared. And so if we're greater than 1 over 2 delta squared, that's now all in terms of constants and deltas. We can just set that equal to m, which gives us, first of all, it gives us delta squared equals 1 over 2m. And then we'll square root both sides of it to give us m is equal to 1 over the square root of 2m. So we'll replace our delta with that 2 times 1 over the square root of 2m squared, which just gives us m. And so our choice for delta is the minimum between 1/4 and 1 over the square root of 2m. So for our next one here, we've got our first N-M proof. So it's an N proof because it's x approaching infinity, and it's an M proof because it equals infinity. And so for the N-M proofs, we start them off with the given like we would with the other M proofs. Right? So our given is going to be, in this case, m is greater than 0, right? Because we're approaching it, or we're equaling infinity. If we're equaling negative infinity, then we'd have m less than 0. And we're going to choose an n equal to something. And so we'll figure out again what that is later. And we'll suppose now, just like for the other n proofs, that x is greater than n is greater than 0 in this case because we have x approaching infinity. And then the goal for the N-M proofs is to prove that your function, no absolute value on it, just your function, in this case is eventually greater than m, where m is written in terms of n and constants. So that's going to be our goal. And if it was equaling negative infinity, we'd be showing that it's less than m in the end. And so to start off with, we need to figure out something to start to clear off the values of x somehow, or to clear off the constants so that we can then cancel out some x's. So the first thing that we're going to do with this one is think about where we want the x's to be. We want the x's to end up in our numerator, right? Because we need inequalities that say greater than, and the relationship between x and n is x is greater than n. So I want to have x's in the numerator here. So let's first try to get rid of the +5 that's in the denominator. And there's a little trick that you kind of want to get used to here. If it's an x plus 5, we want to let x be greater than 5. But since it's x squared plus 5, we want to let x be greater than the square root of 5. And if I do that, then really what I'm doing here is I'm setting a minimum value here for n to be, which means that when I choose n, I need to choose n to be the maximum of root 5 and something else that we're going to figure out eventually, right? And so if x is always greater than root 5, that means that the smallest thing that I could choose for n is going to be root 5. So now what we're going to do here is say that means that x squared must be greater than 5. And if x squared is greater than 5, that's great because that makes these match up down here, right? I have the x squared and the 5. And so I can just add x squared to both sides of this, which tells me that 2x squared is greater than x squared plus 5. And if I do that, we're going to kind of flip this around. That means that x squared plus 5 is less than 2x squared. And we actually have a function over x squared plus 5. So 1 over x squared plus 5 is now greater than 1 over 2x squared. And so now we have a relationship between 1 over x squared plus 5 and 1 over 2x squared, which allows us to say that this is greater than the same numerator there, which is a positive value, divided by 2x squared. And so we're going to start off that way. And then we should also recognize that I can make that numerator bigger in any way I want to, and I would still get a greater than here, right, if I make that numerator bigger. And since I know that x squared is greater than 5, if I were to multiply the 2 in that numerator by x squared, I would certainly be getting something that was smaller than what I have here, right, which is what I want. So right, if I had x cubed minus 2x squared over 2x squared, then I would definitely have a smaller thing there because I've made that numerator a lot smaller, right? Because I'm subtracting a bigger thing. I'm subtracting 2 times something that's more than 5 rather than just subtracting 2 from that numerator. So x cubed minus 2 is a lot more than x cubed minus 2x squared when x squared is greater than 5. So we know this changes. I mean, every time we make a step here, we're changing what function we have, but the function that we have is always something that is less than what we had previously. So ours is always greater, like our starting point is always greater than the next thing. And so now what we can do is we can factor the x squared out of that numerator. Right? If I factor the x squared out of that, I just get x squared times x minus 2 over 2x squared. Well, the nice thing about that is now the x squareds cancel. Right? And that was the goal. That's why I wanted to put an x squared up there so I could factor it out and cancel with the x squared in the denominator. If I just had an x there, maybe I would want, like in the denominator, like a 2x, I would have wanted to multiply that 2 by x in the numerator so I could factor an x out and cancel. So, but now we can cancel the x squared, so we just have x minus 2 over 2. And x minus 2 over 2, which we know is the same as x over 2 minus 1, we can now say is greater than n over 2 minus 1 because x is greater than n. And we'll just let that be our m. And we'll do this work off to the side. If n over 2 minus 1 is m, then that would mean that that n is equal to m plus 1 times 2. Or you could say 2m plus 2 if you want. So we'll say this is equal to 2 times m plus 1 over 2 minus 1, which is, of course, just equal to m. And so what we'll put up here with our root 5 is the maximum between root 5 and 2 times m plus 1. And that is the end of our proof. All right, for our next one here, we've got a limit as x approaches infinity of 3 minus x to the 4th over x squared plus 1 is equal to negative infinity. So again, it's an mn proof, and this time we're going to have given m less than 0 because our limit equals negative infinity. And then we're going to choose an n value equal to something, which we'll figure out in a second. And supposing that x is greater than n is greater than 0 because we have x approaching positive infinity, then we want to show that our function 3 minus x to the fourth over x squared plus 1 is always eventually less than m, right? Because it equals negative infinity, so we want to drop it below that m value that we think our limit might be. So what we're going to try and do here is we're just going to first think about if this thing that we're looking at here is a positive or a negative value, right? So 3 minus x to the fourth, as x goes towards infinity, is certainly a negative, and x squared plus 1 is certainly a positive. So what we're looking at here is a fraction that equals a negative value. And what I'm going to do to begin with is I'm just going to factor out a negative sign from my numerator, just so that I have that kind of in a form that I'm more used to looking at. So I have the opposite of x to the fourth minus 3. And so the x to the fourth minus 3 is sort of like a difference of squares, right? And we might think about one option would be to try and build something into the denominator that cancels with what we have in the numerator. So if I factor that numerator, I have the opposite of x squared plus root 3 times x squared minus root 3, all over x squared plus 1. Now, if I could get either x squared plus root 3 or x squared minus root 3 into that denominator, then I would be able to cancel some terms, and I'd be left with my x's in the numerator, which is actually what we want here. And so if we think about how to do that and which one is actually going to work, the one that's actually going to work is the x squared plus root 3, right? Because I want to show that this thing that I have here is less than something else. And so what we've got, the opposite of x squared plus root 3 times x squared minus root 3, is less than the same numerator with an x squared plus root 3 down here. Because what I've done is I've made the denominator now a larger thing, because root 3 is more than 1. So I've made that denominator larger, but because this thing is negative, right, a larger denominator, which would normally make something smaller, is actually making it bigger because it's a negative, right? So like it's getting to be closer to 0. And so now I can cancel these x squared plus root 3's, leaving me with just the opposite of x squared minus root 3 in here. And then we're going to work with just that, right? And so if you want to, you can rewrite that. Might be easier to just rewrite that now without the negative sign out in front. It's just root 3 minus x squared. And we want then that to be less than something that involves n, which seems like that's not going to work because we know that x is greater than n. But we have to remember that x squared, right? We have x is greater than n is greater than 0, which means that x squared is greater than n squared. But it also means, though, that negative x squared is less than negative n squared. And what we have here is a negative x squared. And so what we'll do is we'll just say now that this is less than root 3 minus n squared. And that is kind of the end of what we have to do here. We just need to let that equal our m value. So we'll do that off to the side. Root 3 minus n squared is going to equal m, which means that if we rearrange this, we'll have root 3 minus m is equal to n squared, or n is equal to plus or minus the square root of root 3 minus m. And of course, we have to decide which one we actually want. Do we want the positive or the negative square root? Well, n has to be positive, so we need the positive square root. So we'll have the square root of 3 minus m, which is what I'll put in here. I'll write root 3 minus, and then the square root of 3 minus m squared. And of course, we can see then that the outer square root cancels with the squared, and we end up with root 3 minus root 3, which cancels, and negative m, which is just m. And so that's the end of that proof. And we've just got one more of these here to go. This is a limit as x approaches negative infinity of negative x squared over x plus 1 equals infinity. So again, it's an N-M proof. Our m is infinity, like, so we want to say given m greater than 0, we need a positive value for m. And we're going to choose n to be something, which we'll figure out again in a minute. And this time we'll have to suppose, since x is approaching negative infinity, we're going to suppose that x is less than n is less than 0. And then we want to show that our function negative x squared over x plus 1 is eventually greater than m, because we want to show that our function goes above any value that we might think its limit is. That's why it's going to infinity. So we need to show that it goes over any real number that we might choose. So we have negative x squared over x plus 1. And if x is going to negative infinity, we'll note that this is a negative value here as x goes towards negative infinity. It's a positive value as x goes towards negative infinity, right? Because we have a negative infinity being squared, which is positive, and then times a negative, and then in the denominator we also have a negative. So we end up this being a positive value. And so if I have a positive value and I want to make it make something smaller, right? Normally we would just remove something from the denominator. But in this case, we have to be a little bit careful about that, because what I really actually want to do is I want to add something into this numerator. Right? I want to add this 1 in here, because what's going on is if I take some number, like for example, let's say, this doesn't make a lot of sense, but since x is going towards negative infinity, let's say, suppose that x was negative 3, right? And I plugged that into each of these. We'd see that if I square negative 3, I get 9. And then I put the negative in front of it. That's negative 9 over negative 3 plus 1, right, which would be negative 2. And then on this side, if I have the negative 9 that I had and I add 1 to it, that's negative 8, right, which is then divided by the negative 2. Because those are positive values, we still end up, right, getting, we get 4.5 is greater than 4. And that should hold true no matter what, because these are all positive values in the end. So just adding something there into that numerator, though, ends up giving us something smaller, which is a little counterintuitive, right? Because it makes this negative number become a number that's closer to 0, but when I divide it by the negative, it actually makes it a smaller number. So I think we can see that inequality looks good. Well, the nice thing now is that negative x squared plus 1 is the same as 1 minus x squared, which is the same as 1 minus x and 1 plus x, which allows us to just cancel the 1 plus x with the x plus 1 in the denominator, giving us just 1 minus x. And if we have just 1 minus x, well, and we know that x is less than n, right? Well, we have negative x, so negative x is greater than negative n. So 1 minus x must be greater than 1 minus n. And, well, that's basically it, right? 1 minus n should be the end of this. We'll just let 1 minus n be our m value, which tells us that n is equal to 1 minus m. So we'll have 1 minus m, which is just m. And so the n that we choose here is just 1 minus m. And that is the end of that proof, which wraps up the last problem here on our more limit proofs homework assignment.